Hello everyone, my name is Michał Skrzypczak and I will present joint work with Damian Niwiński and Marcin Przybyłko. I will talk about regular languages of infinite trees that are definable in weak-MSO logic. So before I move on, let me define the relevant concepts. First of all, our structures are infinite trees. These are functions from sequences of directions to some fixed finite alphabet. So a tree looks like that. It is binary and every node is labeled by some symbol from this alphabet. And now a regular language of those trees is a language definable in MSO, monadic second order logic, which is an extension of first order logic by additional quantifier saying that there is a set of nodes of the tree such that something happens. Together with that quantifier, we have some ways of navigating within a tree. So we can say that one node of the tree is above another or to the left of another. And we can test what is the letter in a given node of the tree. As an example, consider the following formula. We say that for every set of nodes of the tree, if this set of nodes happens to be a branch, so a maximal chain with respect to this vertical order, it is MSO definable. Then for every node on this branch, there is another node on this branch that is deeper and labeled by A. So this formula says that on every branch, there is infinitely many occurrences of A. And now when we have some formula of this logic, it defines a language, a set of trees that satisfy that formula. We can think about it in the following way, that we are in fact interested in languages, in sets of trees, but we need to represent them somehow. And the way to represent the language is to specify it using some formula of the logic. And a very natural fragment of this logic is weak fragment, weak monadic second order logic, where instead of the general quantifier speaking about all subsets, we have another quantifier, the weak one, saying that there exists a finite subset of the domain such that something happens. An example of the formula in this logic is the following. It says that for every finite set of nodes of the tree, there exists a node outside this set, which is labeled A. So this formula says that there is infinitely many A's in the given tree. Now, weak fragment is in fact a fragment of full MSO. It can be proved, and it is strictly weaker. And also other logics relate to those two. First of all, MSO, so regular languages, are the same as those definable in modal mi-calculus. And weak MSO turns out to correspond to alternation-free mi-calculus. So it also witnesses that this weak MSO is a very natural logic, corresponds to the fragment of modal mi-calculus where you have restrictions on how fixed points can overlap. And CTL is quite easily a fragment of this alternation-free fragment of mi-calculus. CTL star is a fragment of full mi-calculus, and of course, first order logic is a fragment of weak MSO. So we have quite a number of logics, but in this talk we will focus on those two, MSO and weak MSO. Now I move to the second piece of definition that we need, namely what does it mean to choose a tree at random. When you look at the space of trees, this is the space of all functions, and it can be seen as a product of copies of the alphabet that we treat as discrete space for each node of the tree. And if you decide to choose each letter in each of these copies separately at random, then you get a probability distribution over the set of all trees that satisfies the property that the probability that a random tree has as some fixed node, some fixed letter A, is exactly the inverse of the cardinality of the alphabet. This is often called coin flipping measure. If you imagine a coin that has as many sides as the alphabet, and you toss this coin for each node of the tree separately, then you get a random tree generated this way. And the problem we are studying in this work is that you're given some specification, some formula phi, and we want to compute the probability that a randomly chosen tree satisfies this property, this formula. So the probability of the language of the formula. And the first difficulty here is that a priori, this probability may not be defined because maybe this language is not measurable. And in fact, it is not entirely ruled out, because there are some non-Borel regular languages of infinite trees. So we don't get for free that every language is measurable, but in fact it is the case. So this probability exists. It is some real number between 0 and 1, but we would like to have some effective ways of computing this number. Before I move on, let me give you an example. In this example, we have the following formula. We say that for every set of nodes that is a branch, there exists a node that is labeled A on this branch. Every node above it is labeled B. So this is the first A on the given branch. And moreover, the depth of this node V is even. This is also MSO definable. So the first A on every branch must exist, and moreover must be at even depth inside the tree. Our alphabet consists of 2 symbols. And now it is quite easy to see that this language is definable in weak-MSO. And also a variant of this language, another language that has the same measure, is even first-order definable. This is due to a very nice example by Pothoff. Now the question is, what is the measure? What is the probability of this language? Let's call it X, some unknown variable. And now, if you think about it, there is 2 possibilities that a tree satisfies that formula. So either the label of the root is A. In that case, it doesn't matter what happens below, and the probability of this event is 1/2. And the second possibility is that the root is labeled B. Then both its children must also be labeled B. And moreover, all the 4 subtrees that we see here must satisfy the same formula. The first A on every branch must be on even depth. And the probability of that event is 1/2 to the power 3, for these 3 letters B here, times x to the power 4, because 4 times we need to satisfy the same property. When you solve this equation, it has 2 real solutions. These are the solutions. And of course, we need to choose one of them, and it must be that one, because the other one is greater than 1. So we have solved the problem. We know that the probability that a random tree has this property is that number. But if you look at these coefficients here, this number is irrational. So we have a very simple language with irrational probability, but algebraic. And also here we were quite lucky, because we were able to rule out this other probability, but it may happen that you have a similar equation and it has 2 roots that are both numbers between 0 and 1. And then it's not clear which is the actual probability of our language. And somehow this is one of the difficulties that I will show you how to overcome. But let me give you some overview of what is already known. So first of all, for omega regular languages, so for languages of infinite words, the probability of this language is always rational, and it can be quite effectively computed. Moreover, if you want to compare the probability with some fixed rational number, and your language is given by a deterministic top-down automaton, so it is a strict subclass of all regular languages of infinite trees, then it is also doable, and this is the work from 2020. Then Michalecki and Mio proved that the probability is computable for game automata, and it is a self-dualization of deterministic automata. And then the probability is always algebraic, and you can effectively compute it. But all these results that are here at the moment have the property that they deal with somehow deterministic models. So even game automata, they are not closed under union. And it means that in a sense, they correspond to the structure of the tree in a sense in a rigid way. And it simplifies somehow the problem. Then there are some results by Marcin Przybyłko from his PhD thesis that it is possible to compute the probabilities for some fragment of first order logic. And in these fragments, the probability is always rational. And the result I am presenting here says that if your language is given by a weak-MSO formula, then the probability is always algebraic, and it can be effectively computed. Because of the expressive power of weak-MSO and the non-determinism that is there, we hope that this can be used or important for model checking of stochastic branching processes. So we hope for some applications of this result. But let me move to some overview how we obtain this result. So first of all, a weak monadic second-order logic is equivalent in expressive power to alternating automata that have weak parity condition. Such an automaton is a finite set of states with some initial state and some transitions saying that if you want to read a letter A from a given state, then you should resolve some Boolean formula. And once it is resolved, you should move to some other state in some direction in the tree, either to the left or to the right in the tree. Now, if you are given a tree over this alphabet, together with this automaton, it produces a game. It is a game between two players. One resolves conjunctions and the other resolves disjunctions. So they go down this arena, playing over these Boolean connectives here. And the winning condition of this game is given by the automaton, because the automaton is split into layers. There are some rejecting layers that are dashed here, and others are called safety layers. And what is important is that the transitions of the automaton always go back the layers. So we either stay in the same layer or go down. We either stay or go down, etc. And now in this game, as I said, it is played between these two players, and the disjunctive player, the one who wants to prove that the tree is in the language of the automaton, wins if only finitely many times they see those rejecting states. So from some moment on, they need to stay in one of the safety layers of the automaton. And now the definition of the language of the automaton is given in terms of this game. So a tree is in the language of the automaton if this disjunctive player can prove it by having a winning strategy in the corresponding game. So now I will give you some simple case of our construction where the automata are safety. So they have only two layers. One is the safety layer where all the states are, and there is the rejecting layer with only one state. Once we reach this state, the disjunctive player loses. So we need to avoid reaching that state. Of course, for more complex automata with more layers, the construction is more involved and it requires some induction over the structure of the automaton. But let's look at this particular case. In this case, there is a very natural definition of an approximation of the language. If you fix some depth d, then you can define the language of the automaton with depth at least d, and this is the set of trees such that the disjunctive player has a strategy in the game induced by this automaton that guarantees not to see bottom in the first d levels of the tree. So until we see the d symbol of the tree, we are supposed not to see any bottom. Of course, later there may be some bottom. So now if you look at this definition, it is quite clear that the languages are monotone. So the language with depth 0 is a superset of the language with depth 1, etc. And our language is somehow in the limit. And because of the Koenig's lemma, in fact, this last inclusion is an equality. So the language is in fact the intersection of all these approximations. In other words, if over some tree, the disjunctive player can win seeing arbitrarily long no bottom, then the disjunctive player has a strategy that actually wins in this tree and never sees bottom. This is some application of compactness argument. So this is a way of representing our language via these approximations. But of course, each of these languages is an infinite set of trees, and it doesn't give us any direct way of computing measures of those. So now to have some effectiveness of our construction, we need to shift from thinking about languages to thinking about distributions. And this is based on the following standard concept, that to each tree, you can assign a set of states of your automaton, namely the set of states Q, such that the disjunctive player has a winning strategy in the acceptance game from Q. So we think of Q as being put in the root of our tree, and we want to continue our game from Q down the tree, and the disjunctive player needs to win that game. And the set of states where it is possible is the type of the tree. It somehow contains all the knowledge that we need to know about this subtree. In particular, we can recover our language from this assignment of types, because a tree is in our language if and only if the initial state of the automaton belongs to the type of the tree. So it is a richer structure that in particular encodes our language. Now, based on that, we can somehow lift this definition to the level of probability distributions. So instead of choosing a random tree according to the probability P, we can choose a random set of states of our automaton according to this arrow P function that is defined in the following way. That for a given set of states of the automaton, the probability that this set of states will be chosen is the probability that a randomly chosen tree will have exactly that type. So because it is a push forward of this probability on trees via this function TP, we see in particular that it is in fact a probability distribution. So the sum of probabilities of all sets of states is 1 in total. And now, if you recall this sequence that approximates our language, to each of these models of accepting trees, we can assign a probability distribution over this power set of Q. But now the problem is that although these sets of trees were monotone, here there is no obvious way of saying that one probability distribution is somehow better than the other. This is some difficulty. We would like to compute this object via these approximations, but we don't know how. No, in fact, we know how, because there is a very natural order on probability distributions on sets of states of the automaton, and it corresponds to going down in terms of the inclusion order. So imagine the following distribution that with probability 0.6 chooses this set of states, and 0.3 that, and 0.1 the empty set. And now we would like to decrease some of these sets, to move some pieces of this probability down, for instance, to the following distribution, where a certain piece of probability from here was moved to here, because it turned out that the state Q0 is not good for us for some reason. And also some probability from here was moved down to the empty set. So we would like to have an order on distributions that somehow simulates this phenomenon that some states are not good anymore, and some probability that corresponded to them should be moved down in this order. Another example is the following. Consider the following distributions. In both of them, we choose with probability 1/2 one set of states or another. And here it is quite easy to see that there is no order in this intuitive understanding that we have, because, for instance, some probability from here goes down here to achieve that, but also some probability from here needs to go up to one of the states here. So this distribution is incomparable with that one. So now I'll give you a definition. We say that one distribution is greater than another if for every upward closed family of sets of states, if we take the overall probability of ending up in that family with respect to alpha, it has to be greater than the probability of with respect to beta. This is called probabilistic power domains, and it was studied in the 80s. And this is quite easy to see this, how this order works. For instance, consider these following two distributions, alpha and beta. We would like to check if there is order between them. So for that, we need to consider all the possible upward closed families, like that, U. Whenever it contains some set, it contains all the sets that are bigger. And we need to sum the probabilities. So in this case, the sum is 0.6. In this case, the sum is 0.5. And of course, there is order between them. So when we take all the possible U's, we see that alpha is greater equal than beta. This is an order. It has very many nice properties. But in particular, it realizes this definition that one probability is greater than another if some probabilities go down, because some states are no longer good from our perspective. Now, if we recall this sequence of approximations of our language, it corresponds to a sequence of distributions, and it is quite easy to prove that these distributions are in fact monotone, because the only thing that can happen moving from one depth to another is that it will be no longer possible to accept a given tree from a given state with this bigger depth. So we have this sequence, and also we have seen that the language is, in a sense, a limit of these approximations, and it also carries over to these distributions. So the distribution corresponding to the language is the limit of the distributions of those approximations. This limit is taken in the linear space, because each distribution is just an assignment of numbers between 0 and 1 to all the sets of states. There is finitely many sets of states, so this is a very nice linear space, finite dimensional real space. And this limit is understood as a standard limit in that space. So now, using all that, we can prove that the distribution corresponding to our language is definable as a greatest fixed point of a proper operator in this space of all distributions with this nice order that we have seen before. And it is definable using first-order logic. So you can use first-order theory of real numbers that is known to be decidable due to Tarski to define this object. And this is the core of our decidability result. So summing up, our theorem says that if we take a weak parity automaton, or equivalently a weak-MSO formula, then the probability of the corresponding language is always an algebraic number. It is computable, and it is even faster computable if you want to compare it with fixed rational numbers, but also you can get a representation of this algebraic number from that. And the proof that we use to achieve that uses a reduction to Tarski's first-order theory of reals, as I told you, but the core is to have some order on these distributions, and this comes from this theory of probabilistic power domains that I have shown you before. And also, instead of working with this fixed probability P that corresponds to randomly choosing all vertices independently, we can input a measure that is generated by some branching process and compute the measure of our language with respect to that probability distribution given by that measure. And as applications, first of all, I already mentioned that we hope for some applications in probabilistic model checking. This logic is pretty expressive, and our algorithms work in elementary time. But also, because of these approximations and the study of probabilistic power domains, we hope to get some insights into the general problem. For general regular languages, this problem is still open, and it seems to be much more difficult because for general alternating automata, they don't have this structure of layers, of safety layers and rejecting layers. And because of that, the approximations that appear there seem to have much more difficult structures. The chain that appear there may be longer than omega, and this is the source of difficulty for general MSO logic. So this is all I wanted to present you. Thank you very much for your attention, and I hope that we will have a nice discussion during the actual conference.